Welcome back to the deep dive. Today we are going to talk about a specific fantasy. I think it's a fantasy everyone has had when they are sitting in bumper-to-bumper traffic,
Oh, yeah.
just staring at the taillights in front of you. You know the one, you push a button on your dashboard, the steering wheel just retracts into the console, your seat reclines, and you take a nap.
Ideally, waking up exactly when you pull into your driveway
Exactly.
is the ultimate dream of the commute.
It is. But as anyone who actually drives a modern car knows, the reality is a lot more clingy. We have lane keep assist, we have adaptive cruise control, but the car is constantly nagging you.
Right.
Put your hands on the wheel, look at the road.
It's like you're driving with a
nervous instructor.
nervous instructor.
Yeah.
That's a perfect description of where we are stuck right now. In industry terms, that's SAE Level 2 partial automation.
So you're still the captain of the ship.
You are. The car is just a very advanced first mate. We're seeing, tiny steps into Level 3, which is conditional automation.
Right, and the fancy stuff, the Mercedes S-Class, the BMW 7 Series.
Exactly. But that's very limited.
Yeah.
And sure, Waymo is claiming Level 4, but that's only in, specific geofence taxi fleets.
Right. But that gap between the car helps me steer and the car is the driver.
Yeah.
I mean, that's not just a software update. It's a massive technological chasm.
It is. And to cross it, you have to solve two really, really hard problems.
Okay.
First, how does the car physically perceive a chaotic world? And second, and this is the one that keeps regulators up at night, how does the car explain its decisions to us?
And that's what we are unpacking today. We're looking at a really comprehensive survey paper from 2025 titled Exploring the Unseen.
Mm-hmm.
It dives into multi-sensor fusion and explainable AI.
Or XAI, as you'll hear it called.
Right, XAI. Because if I'm going to trust a robot with my family at 70 miles per hour, I don't just want it to work. I want to know how it works. I want to know why it decided to change lanes or why it slammed on the brakes.
Trust is the operative word here. You can't have mass adoption without trust. And you really can't have trust without understanding.
So let's start with the hardware, the senses. When I drive, I'm using my eyes to see the lane lines, my ears to hear a siren, my inner ear to feel if the car is sliding. I'm a multi-sensor machine.
You are.
What's a car working with?
Well, the core argument of the source material is that no single sensor is perfect. If you rely on just one, you have a single point of failure.
Sure.
So engineers use what they call multi-sensor fusion. It's all about redundancy. You need different sensors that cover each other's weaknesses.
Let's run down the list because I think people assume it's just cameras.
Cameras are the starting point because they're the closest thing to human eyes. They give you high resolution, they see texture, and crucially, they see color.
You need to know if a traffic light is red or green.
Right. Or read the text on a detour sign. For that, you absolutely need a camera.
But cameras have the same problems my eyes have.
They do, exactly.
Yeah.
Think about driving out of a dark tunnel into blinding sunlight.
You're blind for a second.
You are. Cameras get that same glare. Or think about a pitch-black country road in pouring rain. Cameras. They just really struggle with low light and visual obstruction.
So to fix that, everyone talks about LiDAR. It's always presented as this kind of magic bullet.
LiDAR is incredible technology. It stands for light detection and ranging. It fires out millions of laser pulses per second and measures exactly how long they take to bounce back.
So it's building this ghostly 3D map of the world.
An incredibly precise one.
Right. So a camera sees a flat picture and has to guess the distance. LiDAR knows the distance.
Down to the centimeter. It knows that pedestrian is exactly 12.5 meters away, not about 30 feet. It gives the car perfect spatial awareness.
There's always a but.
There's always a but. And here it's the atmosphere. LiDAR uses light. So if you're in heavy fog or thick dust or just torrential rain,
The light scatters.
those laser pulses physically scatter off the water droplets or dust particles. The signal gets noisy.
So cameras don't like rain because they can't see. And LiDAR doesn't like rain because the lasers scatter. If I live in Seattle or London, this sounds like a problem.
Which is why we still rely on the old veteran, radar.
The same tech we use to track airplanes.
The very same, just scaled down. Radar uses radio waves. And radio waves have a long wavelength, which means they don't care about rain, snow, or fog. They punch right through it.
It's the all-weather sensor.
It is. And it has a superpower the others don't. The Doppler effect. A camera has to watch an object for a few frames to figure out if it's moving towards you.
Right.
Radar knows the relative velocity instantly. It knows immediately if the car ahead is braking.
But the trade-off is resolution, right? It's blurry.
Massive trade-off. Radar can tell you there is a large metallic blob moving at 60 miles per hour in front of you, but he can't tell you if it's a school bus, a fire truck, or a dump truck.
So you need all three. Camera for color and detail, LiDAR for 3D shape, and radar for speed and bad weather.
And don't forget ultrasonics, those little button sensors on your bumper.
For parking.
Yeah, useless on the highway, but crucial for not backing into a bollard when you park.
Now, one thing that really stood out to me in this deep dive is that the paper emphasizes this isn't just about consumer cars.
Mm-hmm.
We tend to think only about, Tesla or Waymo, but the source material talks about off-road vehicles too.
That is a huge sector. I mean, think about agriculture. John Deere has fully autonomous tractors and tillage machines running right now.
Wow.
Or look at logistics companies like Stratum are making autonomous pallet loaders for warehouses.
Or automated cranes in shipping ports.
Exactly. And the environment dictates the sensor suite. If you're a tractor tilling a dry field, you are creating this massive cloud of dust behind you.
So a camera's
The
blind?
standard camera is blind. LiDAR might scatter, so they might swap in thermal or infrared cameras that can see right through the dust.
That makes perfect sense. A robot crane in a shipping yard doesn't need to read speed limit signs, but it needs to know exactly where a container is in 3D space.
Precisely. There's no perfect sensor suite. There's only the right suite for the mission.
Okay, so we have the eyes and ears, we have the stream of data coming in, but having eyes doesn't mean you can see. You need a brain.
That's the fusion part. You have to stitch these conflicting inputs into one coherent reality. And the paper outlined 3 main ways to do this. The difference is all about when you combine the data.
Let's break these down, because this seems to be where the computational heavy lifting happens. The first one is low-level fusion.
Think of low-level fusion like baking a cake. You take your raw ingredients, the raw pixels from the camera, the raw point clouds from the LiDAR, and you mix them all together in the bowl before you put it in the oven.
So the computer isn't looking at a picture and a radar map separately. It's looking at one giant blended data set.
Correct. The advantage here is that you preserve all the data. You don't lose any of the fine details. If there's some tiny weird-looking object on the road, you're less likely to filter it out as noise.
That sounds the most accurate.
It is usually the most accurate for detection. But the cost is massive. You need a supercomputer in the trunk to crunch raw pixels and laser points simultaneously in real time. It creates high latency.
And latency is bad when you're moving at 100 feet per second.
Very bad. Also, it's incredibly sensitive to alignment. If your camera vibrates just a millimeter out of sync with your LiDAR, the whole fused image becomes a blurry mess.
Okay, so what's the alternative? High-level fusion.
High level is like a committee vote. The camera does its own processing and says, I see a pedestrian. The radar processes his data and says, I see a moving object. The LiDAR says, I see a cylinder shape.
And then a central computer looks at those 3 conclusions and votes.
Exactly.
That sounds way faster. You're not sending raw data, just the answers.
It's much faster, much more modular. If the camera breaks, the radar and LiDAR can still vote. But the downside is you lose context.
Give me an example of that.
Okay, say you're driving at dusk. The camera is only, let's say, 40% sure it sees a deer. To keep false alarms down, the camera software might have a threshold of 50%. So it decides, nope, not confident enough, I won't report it. The central brain never even hears about the deer. It's filtered out before the vote can even happen.
So low level keeps the detail but is slow. High level is fast but might miss the subtle stuff. I assume mid-level fusion is the Goldilocks solution.
It is, pretty much. Mid-level or feature-level fusion extracts specific features, first things like edges, corners, motion vectors, and fuses those. It's a balance most modern systems are striving for, and they're mixing this with deep learning to try and get the best of both worlds.
But here is where the story gets a little scary. We have these incredible sensors, we have these complex fusion brains, and yet the cars still get confused. We have all heard about phantom braking.
It's the #1 complaint for a lot of AV owners. You're just cruising down an empty highway and suddenly the car slams on the brakes for no reason.
The source paper actually explains the physics of this, and it's fascinating. They call it multipath propagation.
It sounds like technobabble, but it's really just geometry. Radar signals bounce. Imagine you're driving into a tunnel. There's a metal guardrail on your right.
Okay.
The radar signal hits the guardrail, bounces off it at an angle, hits a stalled car in the breakdown lane, and then bounces back to your car.
So the signal took a longer path to get back.
Right. And because radar calculates distance based on time of flight, the computer thinks that stalled car is further away than it is. Or worse, The angle makes it think the object is directly in front of you.
So the car hallucinates an obstacle.
Clutter, or ghost objects, is the technical term. The car thinks there's a wall in the middle of the highway, so it does the safe thing. It hits the brakes.
And while that's safer than not braking, it absolutely destroys the driver's trust.
Completely. But there's a deeper problem than just bouncing radar waves. It's the brain itself. We're increasingly relying on deep neural networks, DNNs, to process all this data.
And these are the famous black boxes everyone talks about.
Yes. These networks are incredibly powerful. They can learn from millions of hours of driving footage, more than a human could experience in 10 lifetimes. But the trade-off is opacity.
Meaning, we know the input, the image of the street, and we know the output, turn left, but we have no idea what happened in the middle.
Correct. The decision is distributed across millions of artificial neuron connections. If the car crashes, you can't just open the code and find a line that says, if tree, then crash. It just doesn't work like that.
And this leads to some really bizarre vulnerabilities. The paper mentioned adversarial attacks. This sounded less like a glitch and more like a heist movie.
It's terrifying for security researchers. Because these networks look for mathematical patterns that humans don't see, they can be tricked by patterns humans would just ignore.
The example was the sticker, right?
The sticker attack. Researchers found that if you print a specific, seemingly random pattern on a sticker and slap it on a stop sign.
To me, it just looks like a vandalized stop sign. I'd still stop.
To you, it's a stop sign with some graffiti. To the convolutional neural network, that sticker might mathematically disrupt the features it uses to identify a stop sign. It might misclassify it as a speed limit 45 sign.
Whoa. So the car sees a stop sign, thinks it says go 45, and accelerates into the intersection.
Exactly. And because it's a black box, we don't intuitively know why that specific sticker worked. We just see the catastrophic result.
This brings us to the second half of the paper. If we can't just read the code to fix these problems, we need a new set of tools. We need explainable AI.
XAI. It's essentially the translator between the machine brain and the human user. The goal is to make the black box transparent, or at least interpretable.
Now, the paper distinguishes between white box and black box models. White box sounds like what we want.
Well, white box just means transparent logic. Think of a decision tree. If speed is greater than 30 A&D distance to car ahead is less than 5 meters, then brake.
I can read that. I get that.
You can look at that and understand it instantly. We can't drive a car with simple if-then rules, can we? Real traffic is chaos.
No way.
Exactly. White box models are interpretable, but usually too simple to handle the nuance of driving in, Rome or New York City. Black box models are accurate enough for the chaos, but we don't understand them. XAI is about applying tools to peek inside the black box.
Okay, let's talk about those tools. One of the most visual ones they mentioned was saliency maps.
Saliency maps are great. Imagine you're watching the video feed from the car's camera. XAI overlays a heat map on top of it. And that heat map glows red on the parts of the image the AI considers important for its current decision.
So if the car is stopping for a pedestrian, the pedestrian should be glowing red.
Exactly. But imagine the car stops, and you look at the saliency map, and the pedestrian is dark, but a tree on the side of the road is glowing bright red.
That tells the engineers, hey, the AI isn't looking at the person, it's reacting to the tree.
Right. It means the AI learned a false correlation. Maybe in the training data, that specific type of tree only ever appeared near stop signs. The saliency map reveals that error in logic.
They also mentioned more mathematical tools like LIME and ESHAP.
Those are technically feature importance tests. Think of it like an interrogation. The tool asks the AI, okay, you identified this as a stop sign. Was it because it's an octagon? Was it because it's red? Was it because of the white letters?
And how does it do that?
By digitally tweaking the image. It might turn the sign blue and ask, is it still a stop sign? If the AI says no, then we know color is a critical feature. If it says yes, then we know the shape matters more.
It helps you figure out what's driving the decision.
It does. And that leads to counterfactuals, which I love because it's basically how I argue with myself in the shower. The what-if game.
Right.
It's the what-if engine. If the pedestrian had been 2 meters further back, would I still have braked? If the answer is no, then distance was the deciding factor. It helps build a narrative.
The paper actually gave a great example of converting this complex math into a sentence humans can read. They called it a Bayesian rule list.
Right. It took the complex neural net output and it boiled it down to, if pedestrian is within 5 meters, A&D speed is over 30 kilometers, apply brakes.
Seeing it written out like that is surprisingly comforting.
It is. It moves the decision from the magic box did something to The car followed a safety rule.
And that leads us to the big so what? Why does the average listener who isn't an AI engineer need to care about saliency maps? It seems like inside baseball.
It really isn't. It comes down to trust and adoption. There's a huge socio-psychological factor here. We have a deep-seated fear of the unknown.
Mm-hmm.
If a car makes a move that scares you, swerves slightly, brakes hard, and it can't tell you why, you are never getting in that car again.
And regulators are catching on to this. This isn't just a suggestion anymore, is it?
No, it's the law. In August 2024, the EU AI Act came into full effect. This is a massive shift. It classifies autonomous vehicles as high-risk AI systems.
High risk implies a lot of red tape.
Tons, but necessary red tape.
Yeah.
It means manufacturers can't just ship a black box and hope for the best. They are legally required to ensure transparency.
So if there's a crash.
If an accident happens, they have to be able to explain the system's behavior to investigators. They can't just shrug and say the neural network is mysterious.
So XAI is basically a license to operate now.
It is. And it ties into fairness, too. We touched on training bias earlier. The idea that a car might recognize a pedestrian in a winter coat but miss one in shorts because it was trained in a cold climate.
Which is a terrifying thought.
It is. XAI tools are the only way to prove your system is fair. If you run a saliency map and see that the AI ignores people with certain clothing or skin tones, you can catch that bias before the car ever hits the road.
Now, looking to the future, the source mentions that the industry isn't standing still. They are moving toward end-to-end solutions. NVIDIA has something called Hydra MDP. How does that change the game?
This is the next frontier. So traditionally, we break driving down into stages. Perception first, what do I see? Then planning, where do I go? Then control, steer the wheel. It's a chain.
That makes sense. It's logical steps.
End-to-end throws that out. It attempts to use one giant network for everything. Raw sensor data goes in one side, and steering commands come out the other.
No steps in between.
None.
That sounds very efficient.
It's elegant and incredibly efficient. It sort of mimics how humans drive. We don't consciously calculate coordinates, we just flow.
Mm-hmm.
But it makes the system even more opaque.
Oh.
You lose those clear stages where you can check the work.
So as the tech gets smarter, the black box actually gets darker.
In a way, yes.
Yeah.
Which makes XAI even more critical. The smarter and more integrated the car gets, the harder we have to work to interpret it.
Mm-hmm.
We can't just trust the math, we have to verify the reasoning.
So let's recap the mission we've been on. We started with the raw senses. Cameras, LiDAR, radar, and how they each have blind spots in rain or dust.
Mm-hmm.
We looked at the fusion brain that tries to stitch that messy world together using different strategies.
And we face the black box problem, where the car sees ghosts, gets tricked by stickers, or just makes decisions we can't understand.
And finally, we saw how XAI is the necessary flashlight in that dark room, helping us build the trust we need to actually take that nap on the highway.
That's a solid summary. We're building alien intelligences to drive us to work. We just need to make sure we can speak their language.
Before we sign off, I know you always like to leave us with something to chew on. What's the final thought for today?
I do. This whole discussion about explanation raises a question that I find really challenging. Suppose an autonomous car gets into a situation where a crash is unavoidable. A classic trolley problem scenario.
Okay.
It has to make a life or death decision in a millisecond.
Right.
If the AI makes the statistically correct choice, the one that minimizes physical damage based on pure physics and math, is that enough? Or do we, as humans, require a moral justification that we can understand?
Wow.
Can we accept a machine deciding who lives or dies if it can't explain the why in a way that aligns with human ethics?
That's the difference between being correct and being right.
Exactly. And we haven't solved that yet.
Yeah. Well, on that heavy note, thank you for joining us on this deep dive into the mind of the machine. Drive safe.